Let's study section 1.6, magnetic circuits. 1.6.1, electromagnetism. Electrical current flowing along a wire creates a magnetic field around the wire. That magnetic field can be visualized by showing line of magnetic flux. The magnetic flux are represented using symbol phi. The direction of that field can be determined using the right-hand rule. Imagine using your right hand, wrap a wire. Your thumb points to the direction of the current flow. And your fingers show the direction of the magnetic field. A magnetic field is formed around a conductor carrying current. As shown in the figure B, this is a conductor carrying a current. Then this shows the magnetic field. The current flowing through the coil not only creates a magnetic field in the eye, but also creates a voltage across the coil that is proportional to the rate of change of magnetic flux phi in the eye. Faraday's law of electromagnetic induction. The voltage or the electrical magnetic force is equal to N represents the turns of the coil and multiply d phi is the field flux divided by dt. This voltage is called an electromotive force or EMF and is designated using the symbol E. Section 1.6.2, magnetic circuits. The driving force is called the magnetic motive force, designated by epsilon. The magnetic force is created by wrapping N turns of wire carrying current I around a coil core. By definition, the magnetic force is the product of the current multiplied the turns. Its unit is called ampere turns. The left side shows the electrical circuit. The right side shows the magnetic circuits. As we can see the difference between them. Electric circuit is a voltage source is imposed on the two sides of an iron that create current flowing through the iron. The magnetic circuit is a current source change over time through the toroidal core and then create a magnetic field in the eye. It also creates a voltage across the core The voltage is called magnetomotive force. The response to that magnetomotive force is creation of magnetic flux, phi, which has a unit of Webb. The magnetic flux is proportional to magnetomotive force and inversely proportional to a quantity called reluctance R. So the Ohm's law of magnetic circuit, epsilon is equal to R multiply flux phi. Reluctance depends on the dimension of the coil as well as its materials. So the reluctance R is equal to L divided by mu multiply A. Mu represents the permeability, A is the cross-sectional area, and L is the length of the ion. The unit of reluctance R is ampere turns per Webb. It's write as A multiply T divided by WB. How readily the coil material accept magnetic flux is the material's permeability mu. There are three categories of magnetic materials: diamagnetic, paramagnetic, and ferromagnetic. Diamagnetic is the material tend to exclude magnetic field. Paramagnetic, in which the material is slightly magnetized by the magnetic field. Ferromagnetic are materials that are very easily become magnetized. The permeability of free space is given as mu0, which is equal to 4 multiply pi multiply 10 minus 7. Materials are characterized by their relative permeability, μr. For ferromagnetic material, maybe it's in the range of hundreds to hundreds of thousands. So the μr is equal to mu divided by mu0. The magnetic flux density, B, is equal to phi divided by A. Phi represents the flux. A is the cross-sectional area. So when flux is given in Webbers and area A is given in square meters, the units of B, the magnetic flux density, are Teslas. The analog quantity in electrical circuit would be the current density. The electric current density J is equal to I divided by A, which is the current divided by the cross-sectional area. The magnetic field density is defined as the magnetomotive force per unit of length around the magnetic loop. With n turns of wire carrying current I, the magnetomotive force created in the circuit is N multiply I. The units of the magnetic force are ampere turns. When I is represented as the mean path length for the magnetic flux, the magnetic field intensity is therefore defined as H is equal to N multiply I divided by L, where L is the length of the eye. So the relationship between the magnetic flux density B and the magnetic field density H is B is equal to mu multiply H. This slide shows the comparison between the electrical circuit and the magnetic circuit. So analog to electrical, the magnetic circuit have their own quantities. For example, analog to electrical circuit voltage. In the magnetic circuit, we have magnetomotive force. Epsilon is equal to N multiply I, which N represents the turns of the coil. I is the current flowing inside of the coil. The unit of magnetomotive force is ampere turns. Analog to electric circuit current. In magnetic circuit, we have magnetic flux phi. The phi's unit is a Weber, represented using symbol WB. Analog to electrical circuit resistance, we have reluctance in magnetic circuits. The unit of reluctance is ampere turns per Web. Analog to electrical circuit conductivity, we have permeability in magnetic circuits. The unit of permeability is Web per ATM, the ampere turn and the meter. Analog to current density in electrical circuit, we have magnetic flux density, B. The unit of magnetic flux density B is Web per square meter. It's also called Tesla. Analog to electric field in electric circuit, we have magnetic field density H in magnetic circuits. The unit of magnetic field density H is ampere turn per meter. Now we finish section 1.6.